It's Friday morning. The coffee tastes better than usual. The weekend trip you've been planning for weeks is finally here. Your bags are almost packed. There's just one last thing left before you log off, that feature you've been working on all week. You open your IDE, glance over the code one more time, and run the tests. Everything passes. The functionality works perfectly. You feel good about it. You think, let's push this and start the weekend. You create a pull request. Description written. Blue. Tests attached. Code reviewed by yourself twice. You hit submit. Now you wait. 5 minutes later, a notification pops up. Your reviewer is fast. You open it, expecting a quick, looks good to me. Instead, you read, this implementation doesn't follow the strategy pattern. Consider using it instead. Another comment appears. Object creation should be handled using a factory here. And then the classic one, this could be simplified using a decorator instead of conditional logic. You stare at the screen. The feature works perfectly. The tests pass. But apparently the design is wrong. Suddenly, your relaxing weekend feels slightly further away. If this situation feels familiar, you've already brushed against something important in software engineering, design patterns. So, what exactly are design patterns? Imagine building software the way cities build infrastructure. Every city needs roads, bridges, intersections, and traffic lights. Engineers don't reinvent these structures every time they design a new road. Instead, they rely on proven architectural solutions that have worked reliably for decades. Software faces the same reality. As systems grow, developers repeatedly encounter the same kinds of problems. How should objects be created without tightly coupling code to specific classes? How can behavior change without rewriting existing code? How should objects communicate without creating tangled dependencies? Over time, experienced engineers realized that these problems keep repeating. And more importantly, the solutions repeat too. Those recurring solutions are what we call design patterns. A design pattern is not code. This is one of the first surprising things you discover. A design pattern is not a library. It's not a framework. It's not something you import. Instead, it's a well-known way of structuring code to solve a common design problem. Think of it as a blueprint. Just like an architect might say, we'll use an arch structure here. A software engineer might say, let's use the observer pattern here. Immediately, experienced developers understand the structure of the solution. Why do developers care so much about them? Because software doesn't stay small. The real challenge in engineering isn't writing code that works today. It's writing code that still works when the system doubles in size. 5 more developers join the project, requirements change next month, or new features keep piling up. Without good design, software slowly becomes what many teams fear most: rigid, fragile, and difficult to change. Design patterns exist because they help avoid exactly that. They encourage designs that are flexible, extensible, easier to maintain, and easier for other developers to understand. They also create a shared language. Once you learn patterns, conversations about architecture suddenly become shorter and clearer. Instead of explaining a long design idea, someone might say, let's apply the strategy pattern here, or this should probably be a factory, or even we can wrap it with a decorator. To someone unfamiliar with patterns, these sound mysterious. But to experienced engineers, these names instantly communicate an entire design approach. It's like a shorthand for complex ideas. Imagine this, it is your 3rd week on a new project. You open the codebase, and within an hour, you notice something familiar. Different module, different team, different domain, but the same pane appears again, objects are tightly coupled, change in one place breaks another, and every feature request feels expensive. Now rewind 6 months. You were on another product, and you solved almost the same issue. Back then, you introduced a clean way to create objects without hardwiring dependencies. It worked. Everyone was happy, but that knowledge stayed in your team chat, in your head, and in a few comments nobody reads. Fast forward to today. Another team, same class of problem, same trial and error cycle. This is exactly where design patterns were born, not from theory first, but from repeated real-world battles. Across projects and organizations, developers kept running into recurring design problems. Different business rules, same structural headaches. Over time, people started noticing that certain solution shades kept working. Instead of reinventing every time, they began documenting those successful approaches in a reusable form. That reusable form is what we now call a design pattern. Think of it like this. If software development is city building, a pattern is not a finished building. It is a proven blueprint for solving a common structural need, like connecting 2 roads safely, handling traffic flow, or expanding neighborhoods without chaos. So when you hear pattern, don't imagine copy-paste code. Imagine an architectural template, a repeatable way to arrange responsibilities between classes and objects so your system stays flexible under change. Here is the key discovery you should carry with you. First, design problems repeat across systems. Second, patterns capture proven solutions. And third, patterns are architectural templates, not final code. Let's make this practical. Suppose you need one shared configuration object across your app. Team A writes custom guards. Team B uses global variables. Team C creates hidden constructors. Eventually, someone documents the clean, consistent approach. Now, new teams start from that proven structure instead of guessing. That moment, from repeated pain to shared reusable strategy, is pattern emergence in action. This is why patterns matter to you as a developer. They get you a common language with teammates. Instead of saying, that thing where one object updates many listeners, you can refer to a known pattern structure and move faster in design discussions. When should you use patterns? Use them when you recognize a recurring problem shape, when ad hoc fixes are piling up, and when you need a solution that is understandable by other developers over time. Do not force a pattern just to sound advanced. Patterns help most when they reduce future complexity, not when they add ceremony. The big idea here is simple. Patterns emerged because developers kept facing the same architectural challenges and chose to preserve what worked. That is the origin story and also your invitation. Notice repetition. Name the pattern, apply the template, and build systems that age gracefully. Imagine walking into your first week on a fast-growing product team. Everything feels exciting. New feature requests are flying in, users are growing, and everyone is coding fast. But within days, you notice something strange. Each developer creates objects differently, wires modules differently, and handles interactions differently. Small changes cause big breakages. Think of this like running a busy restaurant kitchen. One chef buys ingredients randomly, another rearranges the counters every morning, and a third keeps shouting instructions in a different format each hour. The food might still go out, but stress explodes. Software feels the same when recurring design problems are solved inconsistently. This is exactly why design patterns became so valuable. As developers documented proven solutions, a pattern emerged in the patterns themselves. They naturally grouped into 3 buckets based on the kind of problem being solved, not by language or framework, but by intent. That grouping became a powerful mental map. The first bucket is creational patterns. These are about object creation. You use them when object construction starts getting messy, repetitive, or risky. Instead of sprinkling new everywhere and hard-coding setup logic, you control how objects are created. Think of this as a professional kitchen prep station, consistent, deliberate, and scalable. The second bucket is structural patterns. These are about organizing relationships between classes and objects. You use them when pieces need to fit together cleanly, especially when systems evolve. Maybe 2 APIs don't match, or maybe features need layering without rewriting core logic. Structural patterns help components collaborate without becoming tangled spaghetti. The third bucket is behavioral patterns. These are about communication and responsibility between objects. You use them when workflows become hard to follow, who triggers what, who reacts, and who owns decisions. Behavioral patterns give you clear interaction rules, so your code behaves like a well-coordinated team instead of a noisy group chat. Here is the practical way to remember this. If your pain is, how do I create this object safely and flexibly? You're in creational territory. If your pain is, how do I compose these pieces without breaking them? That is structural. If your pain is, how do these objects talk and coordinate over time? That is behavioral. Notice what just happened. You did not memorize a random taxonomy. You discovered it from real pressure points that show up in almost every project. That is the mindset of a strong engineer. Identify the type of problem first, then choose the pattern category, then select the specific pattern. As you continue learning individual patterns, keep this map in your head. Creational patterns control object creation. Structural patterns organize relationships. Behavioral patterns manage communication. When should you use this categorization? Every time you feel design confusion, pause and ask, is this a creation problem, a structure problem, or an interaction problem? That single question cuts through noise, speeds up decisions, and helps you design systems that stay clean as they grow. Picture this. You're building an app with your team, and everything looks smooth in Sprint 1. By Sprint 3, tiny cracks appear. A report module creates PDF exporter directly. Billing creates invoice exporter with extra setup. Notifications create another variation with hard-coded defaults. Nothing is broken, but every feature now starts with a treasure hunt. Where's this object being created and why differently here? You've seen this before. The code works, but change becomes expensive. One constructor change touches 10 files. A new environment means another round of edits. Tests become painful because classes are glued to concrete implementations. Now imagine you made one shift. Instead of scattering new statements across business logic, you route object creation through dedicated creation points. Suddenly, your app feels calmer. You can swap implementations without rewriting workflows. Things gets easier. Features stop colliding. That calm architecture is the heart of creational design patterns. The theme is controlling object creation, not avoiding object creation, controlling it with intention. Think of a restaurant kitchen. You don't walk in and cook your own meal every time. You place an order through a clear interface, and the kitchen handles preparation rules. In software, creational patterns act like that kitchen, consistent, centralized, and adaptable. Here's the discovery path. 1. You notice construction logic is duplicated. 2. Or you realize usage code should not know every construction detail. 3. You separate creation from behavior. 4. You introduce creational patterns where change is frequent. Now the terminology lands naturally. Factory method. Creation is delegated, so subclasses choose the concrete type. Abstract factory. Create related object families, like UI widgets per theme, without mixing incompatible parts. Builder. Assemble complex objects step by step, especially when many optional parameters exist. Prototype. Clone pre-configured objects when fresh construction is costly. Singleton. Guarantee one shared instance when exactly one is truly needed. When should you use these? When constructors are getting complex. When switching implementations should not affect business flows. When environments differ, dev, test, prod. When you want clean dependency replacement in tests. When not to. If object creation is trivial and unlikely to change, keep it simple. Patterns are tools, not decoration. Your key takeaways. Reduce tight coupling. Classes depend less on concrete implementations. Centralize object creation. Fewer surprises, easier maintenance. Improve flexibility. Your system evolves with less rewrite pain. So next time you type new, pause for 1 second and ask, should this class create this object, or should creation live in a dedicated strategy? That one question is often the turning point from fragile code to scalable design. Imagine shipping your first serious Java backend. Everything looks clean, tests are green, and you feel unstoppable. Then production traffic hits. Suddenly, logs are duplicated, configuration values disagree between modules, and your database connection pool seems to be created again and again. You don't have one app behavior anymore. You have many tiny competing versions of it. In that moment, you might ask, why are parts of my system acting like separate worlds when they should share one truth? That question is the doorway to the singleton pattern. Think of a city traffic control room. You don't want 10 control rooms giving different signals. You want one trusted control center and everyone in the city can reach it. In software, you often need the same thing, one instance, shared everywhere, reliably. This is exactly where the singleton pattern shines. It ensures a class has only one instance and gives global access to it. To build it step by step in Java, first, make the constructor private so no one can create objects from outside. Second, keep a private static reference to the single object. Third, expose a public static method like getInstance to return that object. In real projects, this is common for services like configuration managers, logging services, caching coordinators, and connection managers, places where you want shared access and consistent state. There is a practical catch that beginners often miss: thread safety. If two threads call getInstance at the same time, you might accidentally create two objects. To prevent that, use a thread-safe approach: eager initialization, a synchronized accessor, double-check locking with the volatile keyword, or the cleanest method in Java, an enum singleton when appropriate. So, when should you use singleton? Use it when exactly one instance is a business requirement, when many parts of your app must access the same service, or when shared state must stay consistent. When should you avoid it? Avoid it if it hides too many dependencies, if it makes testing hard because global state leaks between tests, or if you might need multiple instances later. A good rule is to use singleton intentionally, not by habit. Let's name the core terminology clearly: single instance. Only one object exists for that class. Global access point. Everyone gets that same object through getInstance. Private constructor prevents outside instantiation. Lazy initialization. Create the instance only when first needed. Thread safety guarantees one instance even under concurrency. The pattern is not just about having one object, it's about protecting shared truth in your system. You start with chaos. Many competing copies of the same service and end with one trusted source, reachable from anywhere and predictable under load. That journey is the heart of the singleton pattern. Imagine you are building a food delivery app. At first, everything feels simple. One city, one payment provider, one notification service. So, you directly call constructors everywhere. New Stripe gateway, new SMS notifier, done. 2 months later, your app expands. A new city needs a different payment partner. Another market bans SMS and requires WhatsApp notifications. Suddenly, your clean code turns into a maze of if-else blocks. Every new provider forces edits across multiple classes. You are no longer adding features, you are hunting constructors. That is the moment you feel a design problem, not a coding problem. What you really want is this: your checkout flow should ask for a payment gateway, not Stripe specifically. Your notification module should request a notifier, not Twilio SMS exactly. In other words, the part that uses objects should not decide which concrete object gets born. That decision should live in one focused place. Once you separate usage from creation, your code starts breathing again. New provider? Add a new creator? Existing business logic? Mostly untouched. This shift feels small, but it changes the way your system grows under pressure. This is where the factory method pattern enters. Instead of calling constructors directly, you define a factory method, usually in a base class or interface, that returns a product type. Subclasses or dedicated factory classes decide the exact implementation. For example, payment factory can expose create gateway. India Payment Factory returns Razorpay Gateway, while US Payment Factory returns Stripe Gateway. Your checkout service works with the Payment Gateway interface only. It never cares which class was instantiated. That is encapsulated creation, object birth is hidden behind a clear method, and your core flow stays clean. Now notice the 2 big wins you get immediately. First, better extensibility. When tomorrow brings Crypto Gateway or Bank Transfer Gateway, you extend factories or add new ones without rewriting checkout internals. Second, reduced coupling. High-level modules depend on abstractions, not concrete classes. That means fewer ripple effects, easier testing, and safer refactoring. You can even swap fake gateways and tests through a test factory with 0 production hacks. Use factory method when object creation varies by environment, tenant, region, or runtime rules, and when you expect those variations to grow. So if your codebase currently feels like a control room filled with switches, every new feature toddling constructor choices in 10 places, pause and redesign the creation step. Start small, pick one unstable area, define a product interface, introduce a factory method, and root object creation there. Then, watch how your code conversations change. Instead of asking, where else did we new this class? Your team asks, which factory should supply this behavior? That is a huge mindset upgrade. You are not just hiding constructors, you are protecting change. And in real projects, change is constant. Factory method gives you a practical way to welcome that change without chaos. Once you experience that calm, you will reach for this pattern anytime creation rules keep shifting. That is exactly how scalable systems stay flexible while teams move fast, clear creation boundaries, stable business logic, and confident extension. Imagine you are on a food delivery app late at night building your perfect burger. You pick the bun, swap the patty, add double cheese, remove onions, add jalapenos, choose sauce, select a side, select a drink, and then remember you also want gluten-free bread. Imagine if the app forced you to choose everything in one giant form, in one fixed order, with a massive submit button called Create Burger, containing 18 parameters. Sounds painful, right? Now shift that feeling to code. You start with a simple user profile object. At first, it has a name and email. Easy! A month later, product asks for phone, time zone, language, notification preferences, avatar URL, address, privacy flags, marketing consent, and more. Suddenly, your constructor becomes a monster. You can't remember parameter order. You pass null too often. Bugs appear because true, false, true means different things depending on position. Reading object creation feels like decoding a puzzle. That frustration is exactly where the builder pattern shines. Instead of constructing a complex object in one huge step, you build it gradually, step by step, like assembling your burger. You call readable methods for each piece you care about, and then finish with build. In Java, the common flow looks like this. First, userprofile.builder, builder equals new userprofile.builder, passing in Asha and asha@email.com. Then, optional steps, .phone, .timezone, set to IST, and .marketingconsent, set to true. The final step, .build, returns the finished user profile. Now let's introduce the key terminology. The product is the final complex object, the user profile. The builder is the class that collects construction steps. The concrete builder is the actual implementation doing the work, and the director is an optional helper that enforces a specific construction sequence for common presets. There are several reasons why this pattern is preferred. First, readable construction. Your code starts to read like a sentence. You instantly see what is being set and what is intentionally left default. Second, it handles many parameters safely. No more guessing constructor order. Named method calls replace positional chaos. Third, it supports immutability. You can make the final object immutable. All fields final, no setters. The builder does the temporary mutation. The product stays stable after creation. When should you use builder? When an object has many optional fields. When constructors are becoming overloaded and confusing. When you want immutable objects but still need flexible creation. And when you need different recipes for creating related variants. Quick caution. Don't use builder for tiny objects with too simple fields. It adds ceremony you don't need. Use it when complexity is real. So here's the big idea. The builder pattern is not about writing more code, it's about writing code that you can understand in 5 seconds. You move from, did I pass arguments correctly, to I can clearly see what I am creating. That shift improves reliability, readability, and team confidence. And once you feel that clarity, you'll notice something powerful. Complex object creation stops being a risk and starts feeling intentional. Picture this. You're building a food delivery app. At first, everything feels clean. One class handles orders, another handles payments, another sends notifications. Then a new requirement lands. Support partner restaurants with their own billing APIs, loyalty systems, and delivery tracking. Suddenly, your once neat code starts looking like tangled charging cables. You patch one integration, and 3 unrelated features break. You add one new provider, and you touch 10 files. You start feeling that fear every developer knows. If I change this, what else will explode? That moment is exactly where structural design patterns become your rescue team. Structural patterns are about how you arrange classes and objects so they work together smoothly without becoming tightly glued together. Think of them as smart connectors. Instead of rewriting your whole app each time something changes, you build flexible relationships. The codebase grows, but it still breathes. Let's build this intuition step by step. First, you meet Adapter. You have your app expecting one interface, but a restaurant partner gives you another. Adapter acts like a travel plug converter. Same electricity, different socket. You keep your app code stable while integrating new systems quickly. Next comes Facade. Imagine your checkout flow calling inventory, payment, tax, coupon, and invoice services directly. That's noisy. Facade gives you one clean entry point, like a checkout service, hiding the messy orchestration behind a friendly front desk. Then there's Decorator. You want to add gift wrapping, priority delivery, or insurance to an order, sometimes together, sometimes separately. Instead of creating endless subclasses, Decorator lets you stack behaviors dynamically. You wrap objects with features, like layering toppings on a pizza. Now think about tree-like structures, categories, menus, folders, UI components. Composite lets you treat a single item and a group of items the same way. Your code can call render on one button or an entire panel without caring which one it got. As systems scale, another issue appears. One abstraction, many implementations. That's where Bridge helps. It separates high-level logic from low-level details, so both can vary independently. Your notification feature can evolve separately from email, SMS, or push providers. You may also need controlled access. Proxy stands in front of a real object to add lazy loading, caching, security checks, or remote access handling. And when memory becomes expensive, Flyweight helps share common data across many objects instead of duplicating it everywhere. So when should you use structural patterns? Use them when your code is becoming rigid, integrations are multiplying, class hierarchies are exploding, or architecture feels harder to reason about than the business problem itself. Their core promise is simple: promote composition, improve modularity, and simplify architecture. You stop welding parts together and start designing with interchangeable building blocks. That's when your system becomes easier to extend, safer to change, and far more enjoyable to work on. Imagine this. You're on a deadline, demo starts in 1 hour, and your app is ready, except for one thing. Your clean new checkout module expects a payment processor interface with a method called payAmount. But the only gateway your company already paid for is an old SDK with make transaction value. Same purpose, different language. Your code and the SDK are standing face to face, both useful, both correct, and still unable to talk. You've probably felt this pain before, not because your design is bad, but because software lives longer than plans. Teams change, APIs evolve, vendors lock formats, and suddenly you're integrating pieces that were never designed to meet. So, what do? Rewrite the legacy SDK? Risky and expensive. Change your new module to match old APIs everywhere? You just spread technical debt across your codebase. Build custom conversion logic inside business classes? Now your core logic is polluted with integration mess. Here's the turning point. Instead of forcing either side to change, you introduce a small translator in the middle. That translator is the adapter pattern. In simple terms, an adapter lets incompatible interfaces work together by converting one interface into another your system expects. It's like a travel plug adapter. Your laptop charger is fine, the wall socket is fine, but without a tiny converter, no power flows. Let's map the terminology you'll use in Java, the client, the code you wrote, expecting a familiar interface. The target, that expected interface, like payment processor, the adaptee, the existing class with a different interface, like legacy gateway, and the adapter, the bridge class that implements target and internally calls adaptee. So when your client calls pay 100, the adapter translates it to make transaction 100 and forwards it. The client stays clean. The legacy code stays untouched. Why this pattern matters in real projects: first, interface translation. You standardize how your app talks, even when third-party APIs are inconsistent. Second, legacy integration. You plug old systems into modern code without dangerous rewrites. Third, reuse existing components. You keep valuable tested classes instead of replacing them. When should you use it? Use adapter when a class you need already does the job, but its method signatures don't match your architecture. It's especially useful while modernizing monoliths, integrating vendor SDKs, connecting microservices with different contracts, or wrapping old utility libraries. A practical tip: keep adapters thin. They should translate, not perform business decisions. If your adapter starts containing domain rules, split responsibilities. Also, name adapters clearly: legacy payment adapter, XML2 JSON report adapter, so intent is obvious. And here's the bigger architectural lesson: great design is not about forcing perfect uniformity. It's about creating safe boundaries where change can happen without breaking everything. So the next time two useful classes refuse to cooperate, don't panic and don't rewrite blindly. Add a translator. That small adapter can save your deadline, protect your architecture, and let old and new systems move forward together. Imagine building a coffee ordering app. A customer starts with a plain coffee, then asks for milk, caramel, whipped cream, and extra foam. Tomorrow, another customer wants dark roast with soy milk and chocolate drizzle. Coding classes like coffee with milk and caramel, or coffee with soy and chocolate causes a clean code base to turn into a menu-sized class explosion. Instead of creating a new class every time someone adds a topping, keep one core object and wrap it with add-ons at runtime. Like a gift, the same box with new wrapping each time, where every wrap adds value without changing what is inside. In software, this is exactly what the decorator pattern does. To build this in Java terms, first, define a common interface, such as beverage, with methods like getDescription and cost. The plain coffee class, simple coffee, is the base object, known as the concrete component. Next, create an abstract wrapper class, like coffee decorator, which also implements beverage and holds another beverage object inside it. This wrapper is the decorator. Because it implements the same interface, anything expecting a beverage can use it. Then, create specific decorators, milk decorator, caramel decorator, and whip decorator. Each one adds behavior. For example, milk decorator.cost returns the wrapped beverage cost plus the milk price. Description appends comma milk. At runtime, you can start with simple coffee, wrap it with milk decorator, wrap it again with caramel decorator, and perhaps wrap it again with whip decorator. Existing classes remain untouched, and there is no need to create numerous subclasses. Behavior is composed dynamically. This approach provides three significant advantages. First, dynamic behavior. Features are added while the application runs, based on user choice. Second, it avoids subclass explosion, preventing a combinational nightmare of class names. Third, it prioritizes composition over inheritance. Instead of rigid class trees, functionality is assembled like building blocks. The decorator pattern should be used when objects need optional features, when combinations are unpredictable, and when extending behavior without modifying trusted core code is required. It is particularly effective in UI systems, stream processing, logging pipelines, and pricing or customization engines. One caution: if overused, too many wrappers can make debugging harder. Keep decorators focused and small, and use clear naming. If inheritance is like buying fixed meal combos, decorator is like building a custom bowl base first, then toppings, exactly as needed. This pattern is flexible, testable, and open for extension without rewriting existing code. Whenever behavior needs to be enhanced step by step without breaking the core object, the decorator pattern is the ideal solution. Imagine this: it's Friday evening and you just want to watch a movie at home. But to start, you need to turn on the TV, switch the input, power up the sound system, open the streaming app, dim the lights, and then adjust volume because the intro music blasts your ears. You didn't plan a movie night. You planned a mini operations workflow. Now bring that feeling into software. You're building a place order feature in Java. One click from the user triggers inventory checks, payment authorization, fraud screening, shipping setup, invoice generation, and notification emails. Each subsystem has its own API, exceptions, and setup rules. Your service class starts clean, then slowly turns into a control room full of switches. At first, you tell yourself, it's okay, I'll just call each module directly. A week later, every new feature has to repeat those same calls in the same order with the same error handling. Suddenly, your code is tightly stitched to 5 different subsystems. Change one module and ripple effects show up everywhere. This is the moment where you discover a better approach. One front door for a complicated building. That front door is the facade pattern. Instead of forcing client code to speak to every subsystem class, you introduce a single class, often called order facade, home theater facade, or something equally clear. The client calls one high-level method like place order or start movie night. Inside the facade, all the sequencing and coordination happens behind the scenes. Let's name the pieces clearly. First, the client, the code that needs work done, such as a controller, service, or UI layer. Second, the facade, the simplified interface with meaningful business-level operations. Third, the subsystems, existing low-level classes that perform specialized tasks. Notice what the facade does not do: it doesn't replace subsystems, and it doesn't hide all flexibility forever. Power users can still access subsystems directly when needed, but most of your code gets a cleaner, safer path. Why teams love this pattern? It simplifies subsystems by giving you one obvious entry point. It reduces coupling because clients depend on the facade, not every internal component. It creates cleaner APIs that reflect user intent instead of technical choreography. When should you use it? When workflows require multiple subsystem calls in a specific order, when onboarding developers takes too long because internals are too exposed, and when you want to shield clients from frequent internal refactoring. In Java projects, facade is especially practical at module boundaries, payment modules, media engines, reporting pipelines, or legacy integrations. It gives you control over complexity without rewriting everything. So next time your code feels like a wall of remote controls, remember, you don't need more buttons. You need one good button. That's exactly what a facade gives you: a calm, simple interface over a busy system. Picture this. You're building a food delivery app. At first, everything feels simple. One class places orders, another charges payment, another tracks drivers, and another sends notifications. Then launch day arrives. A single order update triggers 5 different actions. One tiny change in payment logic breaks notifications. Driver assignment starts depending on pricing rules. Suddenly, your codebase feels less like a product and more like a group chat where everyone talks at once and nobody listens. You've probably been there. This is exactly where behavioral design patterns step in. They are not about creating objects, they are about helping objects talk to each other in clean, flexible ways. Think of them as communication agreements inside your system. Instead of hardwiring every class to every other class, you guide who talks, when they talk, and how much they need to know about each other. Let's build this idea the way you would discover it in real work. First, you notice chaos. Too many direct connections. One object calls 3 others. Those 3 call 6 more, and responsibilities blur. So your first goal becomes clear: manage interactions. Second, you realize confusion comes from unclear roles. Should the order class decide discounts, trigger emails, and call delivery APIs? Probably not. So the next goal appears: clarify responsibilities. Third, requirements keep changing. Today, you send email alerts, tomorrow push notifications, and next week WhatsApp updates. You need collaboration that can evolve without rewriting everything. That leads to the third goal: enable flexible collaboration. Now the terminology starts making sense. Observer helps when one change should notify many listeners, like order status updates reaching customer, UI, analytics, and notifications. Mediator introduces a central coordinator so objects don't all depend on each other directly, like a dispatch hub coordinating drivers, payments, and tracking. Strategy lets you swap behavior at runtime, like choosing delivery fee calculation based on city, weather, or search rules. Command wraps actions as objects, useful for queues, retries, and undo like flows. State changes behavior based on current state, perfect for order lifecycle transitions. Chain of responsibility passes a request through handlers, such as layered validation or fraud checks. When should you use behavioral patterns? Use them when communication logic is becoming more complex than business logic, when classes are tightly coupled, or when small changes trigger unexpected side effects. If your team is afraid to modify one module because 5 others might break, that's your signal. Here's the mindset shift. You're not just writing classes, you're designing conversations. Great systems are not the ones with the smartest objects. They're the ones where objects collaborate clearly, predictably, and change safely. So, as you design your next feature, ask yourself, who should know what? Who should trigger what? Who should stay independent? Those questions naturally lead you to behavioral patterns, and that's how you turn noisy code into coordinated communication. Imagine you are on call for a shopping app launch night. Orders are flowing, users are excited, and then the product team asks for just one small thing. When inventory changes, update the product page, alert the warehouse dashboard, refresh recommendations, and trigger a low stock notification. At first, you do what most developers do. Inside your inventory service, you call product page updater, warehouse notifier, recommendation engine, and alert service one by one. It works for a week. Then marketing adds a back in stock email. Finance wants a demand signal. Analytics wants event tracking. Suddenly, your inventory code knows everybody. Every new feature means editing the same class. You're not writing features anymore, you're untangling knots. Now imagine a different approach. Instead of inventory calling everyone directly, it simply announces, stop changed. Any interested part of the system can listen and react automatically. Inventory does not care who is listening. SNAS can come and go. That shift is the heart of the observer pattern. You can think of it like a channel you subscribe to. One source publishes updates, many subscribers receive them. In pattern terms, the subject, or publisher, is the object with changing state. The observer, or subscriber, represents objects that want updates. Attach and detach are used to subscribe or unsubscribe observers. And notify tells all current observers when state changes. In Java, this often shows up as an interface like observer, with a method void update, taking an event E, and a subject that keeps a list of observers. When the subject changes, it loops through that list and calls update. What's powerful here is not the loop. It's the loose coupling. Your publisher depends only on an abstraction, not concrete services. You can add a new observer without rewriting core business logic. That is why this pattern is everywhere in event systems. UI listeners, message-driven flows, domain events, even reactive pipelines. When should you use it? Use the observer pattern when one state change should trigger multiple side effects, especially when those side effects change over time. If your code has a growing chain of direct calls after every update, that's a strong smell. Quick caution, observers can become noisy if every tiny change emits an event. Keep events meaningful and avoid circular updates where observer A triggers subject B, which triggers A again. So the practical takeaway is simple. 1. Model updates as published events. 2. Let interested components subscribe. 3. Keep publisher and subscribers loosely coupled. You started with a fragile tangle of dependencies. You end with a publish-subscribe flow where multiple objects react automatically to state changes. That evolution is exactly why the observer pattern feels less like a theory and more like relief. Imagine a team building a navigation app. On Monday, users want the fastest route. On Friday evening, they ask for no toll roads. During monsoon season, they want to avoid flooded streets. This involves the same app and the same map, but totally different decision logic. Initially, one might hardcode everything into a single, giant route planner class. A few if-else walks feel harmless, but then 10 more arrive. Soon, every new route rule requires touching old code, retesting everything, and hoping nothing breaks. Instead of shipping features, the focus shifts to negotiating with conditionals. Consider a different approach. Instead of asking one class to know every route rule, give it one job. Ask someone else how to calculate the route. That someone else can be swapped depending on the context. This separation of what is done from how it is done is the core of the strategy pattern. To build this naturally, first, define a common contract, such as route strategy. Each algorithm becomes its own class. Fastest route, strategy, no-toll strategy, and scenic strategy. The main class, known as the context or route planner, holds a reference to a route strategy. At runtime, the strategy is injected or switched based on user choice, traffic data, or subscription tier. The planner does not need to know algorithm details, it simply tells the strategy to calculate the route. This approach provides 3 significant advantages. First, runtime behavior change. Logic can be switched while the app is running without rewriting the context class. Second, encapsulated algorithms. Each algorithm lives in its own class, making it easier to test, debug, and reason about. Third, open-closed design. New strategies can be added without modifying stable, existing code. In Java, this implementation is clean and practical. Use an interface for the strategy and implement concrete strategy classes as strategy objects through constructor injection or setter methods. Optionally, combine this with dependency injection frameworks when strategies are selected by configuration. The strategy pattern should be used when repeated conditional branches select one of many behaviors, especially when those behaviors evolve independently. It is ideal for payment systems involving cards, UPI, or wallets, as well as pricing rules, sorting methods, notification channels, and compression formats. However, avoid this pattern if there is only one fixed algorithm with no near-term variation, as it may add unnecessary classes. Think of the strategy pattern as giving code a plug-in brain. The context remains stable while the intelligence becomes replaceable. This shift moves away from coding a single smart class toward designing a system where behaviors are first-class citizens that can be swapped at will. Once this freedom is realized, strategy opportunities become apparent everywhere. You're rushing out for work, coffee in one hand, laptop bag in the other, and you say, "Turn off all lights." Instantly, your smart assistant handles it. Later, you remember you left the porch light on, so you tap undo in the app, and that one light comes back. You didn't manually call each bulb. You issued an action, and something else executed it. Now imagine your codebase without that structure. Your UI button directly calls a light object, your keyboard shortcut calls a different method, and voice commands call yet another path. Then, product asks for command history, delayed execution, and undo. Suddenly, every trigger knows too much, and every feature touches everything. That's the pain the command pattern solves. Instead of passing around who should do what right now, you package a request into an action object. In this pattern, that object is called a command. It usually has methods like execute and, when needed, undo. Let's build this step by step. First, you have a receiver, the real worker, like light text editor or bank account. Next, you create a concrete command, for example. Turn on light command, holding a reference to light. Inside execute, the command calls receiver behavior, like light.on. Finally, you add an invoker, maybe a button, menu item, scheduler, or remote control. The invoker only knows it can run a command. Here's the magic. Your invoker is now decoupled from business objects. A button doesn't care whether it turns on a light, saves the file, or places an order. It just runs command.execute, and now the cool features become natural. Need undo? Store executed commands in a stack. Each command knows how to reverse itself. Need logging? Log command objects. Need queuing and retries? Put commands into a queue and process asynchronously. Same abstraction, more power. Picture a text editor. Typing, deleting, formatting, each operation can be a command. Press Ctrl+8, pop the last command and call undo. Want macro recording? Save a list of commands and replay them. You didn't redesign everything, you reused the same action object model. When should you use this pattern? Use it when you have multiple ways to trigger the same operation. You need undo and redo. You want operation history, auditing, or delayed execution. And you want to keep UI or API layers independent from core logic. Avoid over-engineering tiny flows. If there's one simple call and no future need for history, queuing, or undo, plain method calls are fine. So the core takeaway is simple. Treat requests as first-class objects. That gives you flexible action objects, built-in paths for undo support, and a clean boundary between invoker and receiver. Once you start thinking this way, your architecture feels less tangled and more like a control panel. Every button sends a command, every command knows its job, and your system becomes easier to extend without breaking what already works. Think about that exciting first week of a new project. You open your editor, create a few classes, wire things together, and everything feels clean, fast, and simple. you feel unstoppable. Now, imagine building a ticket booking platform for small events. Version 1 is tiny, one event type, one payment option, and one confirmation flow. It works beautifully. Then, real users arrive. One organizer wants group discounts. Another needs seat categories. Someone asks for wallet payments, while another needs QR check-in. Then come refunds and partner APIs. Every request sounds small, but suddenly each change touches code in 3 or 4 places. You patch one thing and another breaks. That moment is your signal. Design patterns are not decorations for code, they are response strategies for recurring structural problems. If a project is still straightforward, simple code is usually better. But when the same design pain keeps returning, patterns become practical. To recognize the right moment, first, look for repeated design friction. This isn't about copy-pasted lines, but repeated architecture pain. Are you repeatedly adding long conditional branches to switch behavior? Are you rewriting object creation logic whenever a new variant appears? Recurring problems are where patterns earn their place. Second, track the direction of change. Ask what changes every sprint. If payment methods, notification channels, or pricing rules keep evolving, you need flexibility. Patterns help isolate what changes from what stays stable, keeping the core flow predictable while letting variable parts extend safely. Third, watch for ripple effects. If editing one class forces updates across unrelated modules, coupling is too high. Patterns can reduce those direct dependencies so teams can move faster without fear. However, avoid the trap of premature abstraction. If you have only one payment method today and no sign of change, building a full strategy hierarchy might be over-engineering. If object creation is trivial, a factory might add ceremony without value. Patterns should remove complexity pressure, not introduce it. Use this simple test. Is this problem recurring? Is flexibility required now, not maybe someday? Will this pattern reduce future change cost more than it increases present complexity? If the answers are mostly yes, it is time for a pattern. Think of patterns like expandable furniture in a small apartment. You do not buy foldable systems for a one-time guest, but if guests come every week, that flexibility transforms your life. The core mindset is to listen to the codebase rather than chasing patterns. When you notice recurring structural pain, rising change pressure, and costly ripple effects, apply patterns deliberately. Use them as tools, not trophies. When you do, the code stops feeling fragile and starts feeling ready. Picture this. It's Wednesday evening, release day is Friday, and you just need one simple feature. Send a welcome email after user sign-up. Easy, right? But when you open the codebase, you find an email service factory, a notification strategy, 3 interfaces, 2 adapters, and a builder for an object with 4 fields. You spend 40 minutes tracing control flow only to realize the feature still sends exactly one email and exactly one way. If you've ever had that moment, staring at clean architecture that feels anything but clean, you've already met today's topic, when design patterns make code worse. Here's the twist. Patterns are not the villain. Overuses, you start with good intentions. You want flexibility, you want code that can scale. You want to look ahead and avoid rewrites. So you add structure early. Then more structure. Soon, simple logic is buried under layers of abstraction. The code is technically pattern-rich, but practically hard to read, hard to debug, and slower to change. Think about buying kitchen tools. A good chef's knife solves most tasks. But if your drawer is full of avocado slicers, banana cutters, and 6 kinds of peelers, making dinner gets harder, not easier. In software, unnecessary patterns are those extra gadgets. Now let's introduce the terminology. The first pitfall is pattern obsession, forcing a pattern into every problem because it sounds professional. The second is over-engineering, designing for 10 hypothetical futures while ignoring today's actual requirement. Third is readability debt, code that is architecturally impressive but cognitively expensive for the next developer, which is often you in 3 months. So, when should you use patterns? Use them when pain is real, repeated, and visible. First, you have multiple behaviors that truly vary, not just maybe someday. Second, you see duplication across several modules. And third, you need to swap implementations in production, not in imagination. And when should you avoid them? Avoid them when there is only one implementation, one flow, and one clear use case. Avoid them for a feature that's still evolving and not yet stable. And avoid them when a team needs clarity faster than theoretical flexibility. A practical rule you can apply tomorrow: make it work, make it clear, then make it flexible. In that order. Before adding a pattern, ask yourself: 1. What concrete problem does this solve today? 2. What code becomes simpler because of it? 3. Can a new teammate understand this in 5 minutes? If the answers are fuzzy, hold off. Great architecture is not about how many patterns you can name. It's about making change safe and understanding easy. So yes, learn patterns deeply, but wear them lightly. Your goal is not pattern-heavy code. Your goal is code that your team can read, trust, and evolve. That is how you avoid pattern obsession, avoid over-engineering simple problems, and keep readability at the center. Imagine this. It's Friday evening. Your team is racing to ship a feature, and suddenly 3 different modules break for 3 different reasons. You fix one bug and 2 more appear. You're not writing bad code. You're just building without a map. At some point, every developer hits this wall, where effort goes up but clarity goes down. Now picture another version of you, 6 months later. Same pressure, same messy requirements, same last-minute changes. But this time, you pause and think, I've seen this shape before. You don't panic. You recognize the structure of the problem. You know which part should be flexible, which part should stay stable, and where change is likely to happen. That moment is the beginning of thinking like an architect. Architectural thinking is not about drawing huge diagrams or using fancy words. It's about training your eyes to see recurring design situations. At first, design patterns feel like separate techniques. One for object creation, one for behavior changes, one for organizing responsibilities. But over time, they stop feeling like isolated tools. They become instincts. Think about learning to drive in a busy city. In the beginning, every signal feels overwhelming. Later, you naturally notice rhythm, where traffic slows, where pedestrians appear when someone is likely to cut in. Experienced developers do the same with software. You begin to spot signals early, duplicated creation logic, tightly coupled classes, exploding if-else branches, brittle integrations. Those signals whisper, a pattern belongs here. This is where your vocabulary becomes useful. You start naming what you see. We need a strategy here so behavior can vary safely. A factory would clean up object creation. An observer can decouple these event updates. The goal isn't to force patterns everywhere. The goal is to make better trade-offs, faster, with less risk. So when should you reach for patterns? When change is frequent, when responsibilities are muddy, when code is hard to test, or when one class keeps absorbing too many jobs. Patterns help you shape boundaries. They reduce surprises. They make systems easier for teammates to understand, extend, and maintain. And here's the biggest shift. Patterns are not the destination. Mindset is, the more systems you build, refactor, and debug, the more your architectural intuition sharpens. Experience turns pattern knowledge into pattern recognition. You stop asking, which pattern should I use? And start asking, what kind of change is this design preparing for? That is how maintainable systems are built. Not by memorizing diagrams, but by repeatedly connecting problem shapes to proven solutions. Over time, you don't just write classes and methods. You design for evolution. You design for people. You design with intent. If you take one thing from this chapter, let it be this. Every project is training your architectural eye. Keep noticing recurring problems. Keep naming the patterns behind good solutions. Keep refining your judgment. Because when patterns become part of how you think, architecture stops being a role title and starts becoming the way you build software.